see number one is not here, so I guess I go first. So in this project, we're improving pollen classification with lead training effort. Hi, my name is Rich Nguyen, and I'm working with Dr. Min Shin Group from UNC Charlotte. And this project is in collaboration with University of Arizona. So let us start it. So first of all, why do we classify pollen? Right? And so this picture shows you a pollen allergy sufferer and really big sneeze. So we help to develop treatment for allergy, and we also, pollen is very vital for a crop because in trees and plants need pollination services. So let's look at the world of pollens. So the very small microscopic world. The image on the top, the width of the image is actually only 1 millimeter, so very small. And you can see a dense population of pollens, and you can see a crop image from below, so different sort of size and shapes. So we're going to classify 9 of these types. And the goal of the automated classification is to, first of all, extract the active contour from the boundary of each pollen, extract the features, and then classify what type of pollen does it come from. And the goal is you want to achieve high accuracy comparing to the manual labeling effort done by experts. So you want to have really good correspondence to that. And at the same time, you want to require very small, little training effort as well. So what sort of challenge are we looking at here? So it's a labeling effort for the skilled specialists that we want to minimize. So if you do just manual labeling, it's very tedious and expensive, and nobody wants to just sit on the computer all day long and circle around the pollen and determine what type it is. So manual is not a good way to go. Even automatic classification is still require a lot of training effort, because as the number of pollen types go up, like up to 50 types, the number of training samples become very big. And you want to minimize this as much as possible. And that's what we're aiming to do. So how are we going to do this? I have two main points. So first of all, we're going to apply transfer learning to the classification problems. So imagine each of these are existing sample from some type that we collected before, which we have many samples, so this there is existing. And so for a problem like this, any traditional machine learning technique would do just fine. So we use AdaBoost for it and check some sort of rule and decision boundary. But the problem when you have very few target or new training samples, I have only a few, and so how do you want to do this? You apply traditional machine learning technique, you're going to be overfit or underfit, so it's not good. So that's why we modified a transfer learning method for AdaBoost called task AdaBoost, and we're able to extract decision boundary based on the existing rule. Another thing is, since the active contour are fully automated, it's easy to collect a lot of unlabeled samples. But how do you utilize this unlabeled sample to train and improve the classification performance? So we use active learning, and we develop a new selection criteria with the minimization constraint to only select the sample that's closer to the decision boundary that most likely to be target samples, like I selected there. And from there, we ask the expert for labels, and then improve or update the decision boundary based on the new training data set. Okay, so they update the decision boundary of the rule. So how do we evaluate our classification methods? We run 2 experiments. In the first experiment, we want to test whether our method select more target or training samples. So you can see the image on the left. The y-axis is the accuracy, so mean higher is better. And the x-axis is the labeling effort, so you want little is better. So our method in green, and we compare with other 2 methods, is task AdaBoost, which is state-of-the-art transfer learning, published in 2010, and AdaBoost, which is machine learning method. And our method have very high performance, up in the 92, with only about 1/5 of the training effort, so it's quite good. And then we run the second experiment, which is test to see if our method actually not only select more training sample, but better training sample. So our exit now is just so all methods have the same target samples. And again, our method have higher accuracy given the same target sample, which means we select better training samples. So in short, we reduce training effort up to 5 times and achieve 92% accuracy. So, well, I'd like to thank you, all of you, to being here, and we have such a handsome group here, so thank you so much, and my poster is number 22. Thank you.